Hey, this is Jesse with Create This. Today I'm going to take my solar generator that I lovingly refer to as the battery bomb, and I've actually redesigned it recently so that it is no longer a battery bomb in my opinion. I've replaced the internal battery with a Anderson SB350 forklift battery connector, and that 4/0 cable goes to a separate container that contains the actual battery. So the battery is no longer internal, and it has a physical quick disconnect. So I feel like personally that goes a long way towards making this less dangerous of a system, because anytime I have to work on this part of the system, I can physically disconnect the battery, and now there's no longer a risk that I'm going to, arc weld my wrench or something. So anyway, because I've made these changes, there's a possibility that it doesn't stress test as well. Maybe I made a connection improperly, or I failed to tighten something down, or something loosened up because of vibration, because I was moving the case around. These are portable, they're on wheels. So what I'm going to do is I'm going to take this down to the basement. I'm going to take the battery and the main piece that has the charge controllers and the inverter and all of that stuff. I'm going to take it down to the basement. I'm going to pull it out of the Pelican case, and I'm going to put it on a thermal camera, and we're going to apply a very large load to it, probably 1,500 watts or so, and we're just going to stress test it and see if anything heats up where it shouldn't, and sort of evaluate it from a stress testing perspective. So this should be a lot of fun. All right, so to disarm, quote unquote, the battery bomb, all I have to do here is I can turn off the breakers. So this is the solar input. So I'm just going to turn off the breakers for the charge controller and remove the solar input right there. And then I can also turn off the main breaker. So now it is completely disarmed. The only thing that is left on is the Victron battery monitor. And so now it is safe to disconnect the forklift battery connector. And now that system is completely disarmed and it's ready to bring downstairs. So there's an output. That's my battery charging. And these are just to stop the case so that it's propped open a little bit and has some airflow. So they're not really important. You can put those aside. All right. Okay, so one of the excellent side effects of moving the battery out of the unit, the main unit here, and replacing it with this SB350 connector is that we've saved a lot of weight. So the entire system, I used to need an engine crane to lift this out of the Pelican case, and that was a big problem because if I ever needed to perform maintenance on it by myself, if my family was away or something, I wouldn't be able to do that, which, that's kind of a problem. So, and I'm kind of an independent kind of person, and I don't like having to rely on other people to do things. So I did buy an engine crane so that I had that option. But again, a nice side effect is that I can now remove it myself. So this system that I have here with these hooks, this was designed for the engine crane. It's really not ideal for a single person to lift. And also, I unfortunately can't really lift with my legs quite as easily because of the setup. So it sucks. It's less than ideal, but it is doable. So what I do is I grab it at each corner, lift, and just put it right up there. And so now I can just put the Pelican case aside, move on to the battery. All right, so this is the battery. Oh. It's got this nice kind of airport style arm for wheeling it around. So this one comes out of the case quite a bit easier. I got smart and I started using these folding handles. They're quite nice. So you just lift, usually push down a little bit with my fingers, and it comes right out. All right. Okay, so this is the new battery versus the old battery. I just wanted to talk about this a little bit to kind of explain the differences. So the new battery is a 100 amp hour, 12 volt lithium iron phosphate. I pronounce that LiFePO4. That's probably not the accepted pronunciation. I'm pretty notoriously horrible at butchering things like that, but it stands for lithium iron phosphate. So they're both lithium iron phosphate batteries. However, this battery, the new one, the Battleborn, is much more intelligent. It has a built-in battery management system, or BMS. And so what that does is it controls the battery so that if you discharge the battery, it shuts it off and it doesn't burn to the ground. And also, if you charge the battery too much, it also shuts off so that it doesn't burn to the ground. So it protects the battery, and the side effect of that is that you have, almost twice the capacity from this battery versus this battery. Even though they're both 100 amp hour batteries, what I was doing before is I had a bottom balance set up on this old GBS battery. And so I used a low voltage disconnect. This is a Victron BP 220. And so I had this set up so that it would cut off the battery if it was discharged too much. And then I also had my charge controller set so that it would only charge it to about 80% of its capacity, right? So I would never charge it fully. So that was my strategy, right? Because I didn't have an onboard battery management system, I essentially turned this 100 amp hour battery into a 60 amp hour battery. So I lost almost half of the capacity. I lost about 20% on the top end and 20% on the bottom end. So this battery, because it has a battery management system built in, they are rated at a true 100 amp hours usable. So this is a much higher capacity battery, even though it's about the same size. I am really, really excited that Battleborn has started manufacturing these and selling them in the United States, because this is a fantastic solution. So now that I no longer have to bottom balance, all of this was removed from the original unit, and I moved it external into this other casing. And so what I have here is I have these homemade bus bars made out of, I believe, I actually don't remember the thickness of the copper, but this is pure copper. I think it's 3/16, but it might be more than that. I don't remember. They're fairly thick. And I just bent this with a hammer. And then we've got 4/0 cable going to the Anderson SB350 connector. I know that they have bus bar contacts for these, but I wasn't quite sure how I would keep the ends of the bus bar contacts. They're like screw terminals on the bottom. I wasn't sure how I would keep the ends from touching each other because they kind of wobble in the SB350 connector. So I went with the 4/0 cable just for safety reasons, because I definitely don't want any shorts. So, and then I've got my Victron BMV 712 shunt here. And so there's a Victron unit right here. And then on this side, I've got a 120 amp Blue Sea Systems DC breaker. So those are the only things on this setup. It is essentially just a battery, a breaker, and a battery monitoring system. I do intend to probably put some 45 amp Anderson connectors up here, just so that I can take this unit camping as kind of a very small solar system, because I have like an external MPPT charge controller that operates pretty well off of just a single 100 watt hour panel. Single 100 watt panel, I guess, is the proper way to say it. So anyway, I'll probably put 45 amp connectors there just so that I can use it in a lower capacity situation by itself. But what I'm going to do is I'm going to make 4 of these. So this is the prototype. This is the first one. I'm going to make 4 of them, and I'm probably going to set them up in parallel, and then I'm also going to set them up in series, just as kind of an experiment to play with. But for now, this is the first one. Sorry, that was quite a bit of talking. Anyway, let's get on with the stress testing. All right, so I thought at this point it might be useful to give you kind of a detailed view of the main body of the solar generator. So the purpose of this unit is it has an MPPT charge controller. It has the SB350 connector where the battery is attached, the head unit for the charge controller, so this is where you control the charge controller. It's got its own Victron battery monitor, which is really, at this point, just a convenience for me so that I can monitor the state of the batteries, because there's going to be 4 of them in parallel connected to this. So I can just get the state of everything right here. This is a remote control for the inverter. So the inverter is down here. It is a Xantrex 2000 watt SW pure sine wave inverter. So this is the remote turn on for that, and this is the GFCI socket for the inverter. So this is where you plug in your things. And then so the rest of these breakers are just breakers to control various inputs and outputs. So this is a bank of two 45 amp Anderson connectors, and I think the lower two are controlled by this breaker and the upper two are controlled by this breaker. This is a 75 amp Anderson connector, also an output. So this has a 50 amp breaker instead of the 30 amps on the 45 amp connectors. And so sometimes I also use this output because this is DC, right? So everything is kind of bidirectional. Sometimes I also use this output for an input, particularly if I'm charging from an AC wall charger. I'll plug it in here. This little guy here, this is the positive connector for just some standard like car battery lug style connectors, just in case I ever needed to use those, in case I ever needed to put some alligator clamps on it. So there's one there and there's also one over here, but I keep these caps on them to keep accidental short circuits from happening. This is the main breaker for the system. It shuts off everything except the Victron battery monitor. And then this is the input for the MPPT charge controller. And so this breaker controls the input, and then this breaker controls the connection from the MPPT charge controller to the battery. So this is a 60 amp on both sides. So looking inside, it's kind of a rat's nest in there at the moment, but you can see the Midnight Classic MPPT charge controller is on that side. This space right here is where the old GBS lithium iron phosphate battery used to be, and it is pretty much entirely replaced by the SB350 connector, Anderson connector, and also the wires that go to that. So I didn't save quite as much weight as I wanted to because these 4-aught cables are pretty heavy, but it did save a good bit of weight. So you can kind of see on this side, there's the Victron shunt, and underneath these plastic covers are Blue Sea Systems bus bars. And I don't remember the amperage rating on these, but they're very high rated amperage. I can maybe display that on the screen through the magic of editing. Let's go around the back here. So also this is just a fan so that I get some air circulating. Sometimes the MPPT charge controller gets hot, and it does have its own fan, but I don't know. I like to have a way to cool everything off. I originally put this to cool the battery itself, and so this is just the air inlet, and then this is the controller for the fan. And so I've just got, at the moment, where is it? Right there. There's the temperature sensor for the fan. And so it's just automatic. It'll, when it senses that this thing is over a certain temperature, it'll kick on. I think it's just like a PC case fan. It's not a big deal. Okay, and so there's all the wiring on that level. And then down below it, this is the Xantrex inverter. This is the front of the unit. And so the only thing that I've done that's special to this is I actually took it apart and I replaced the GFCI that was on the front here. This used to be a GFCI. In fact, I have it right here. This is what came in that slot. So I just took this out and I replaced it with a socket that does not have a GFCI. And that's a little dangerous, particularly because it's kind of a pain in the ass taking this case off, just the way they've designed it, and then putting it back together. You really have to have attention to detail to do that properly without causing a short. I'm pretty confident that I did it properly, but I would not recommend trying that at home unless you're very good with electronics. It's kind of a dangerous thing to do. But the reason why I did that is because we had a tornado and I was using this to power my refrigerator. when the power was off all across the city for about a week. And when that happened, so remember, all of this is down inside a Pelican case, right? So when that happened, we had the GFCI trip because our refrigerator caused it to trip. I'm not sure if there's a short in the ice maker or what, but when that happened, this GFCI tripped, but also the GFCI down here on the inverter tripped. And remember, all of this is inside a Pelican case, and at the time, I had that giant LiFePO4 battery right here, right? So very heavy, hard to remove, and the only way to reset the GFCI on this thing was to pull the entire unit out of the Pelican case and push the button from the other side. So terrible design on my part, and I instantly regretted that decision. So what I did is I disassembled everything. I took the GFCI off of this, and so it's a little more dangerous because now this cable inside the unit is unprotected, but it's way more convenient for me because now if this GFCI ever trips, there's only one button to reset it. So much more functional and ergonomic from my perspective, if possibly a little bit more dangerous. So it's a risk I'm willing to take, I think. Okay, so let's get on with the stress test. Okay, we're all powered up. Let's get the thermal camera going. Okay, so what I'm doing here is I have this 0.5 liter tea kettle. It's got a plug on the end. It just plugs into a regular socket. And I'm going to plug this into the inverter here. And with this camera, we're going to watch the voltage and amperage. And with the thermal camera, we will watch the temperatures. So perhaps on the thermal camera you can see this. This is the tea kettle right here. Okay, so let's go ahead and turn on the inverter. So the tea kettle should now have power, and we're at 13.7 volts, and we're going to turn on the tea kettle. Hopefully it doesn't burn to the ground immediately. All right, so we immediately dropped from 13.7 down to 12.9392. Let's look at the amps. We're drawing 65 amps or 832 watts. That's pretty awesome. We'll just keep that on voltage for now. I'm going to switch over to the thermal camera here and just kind of watch this whole setup. Go ahead and calibrate this. There we go. So that is clearly getting hot. We can see the inside of the inverter getting a little warm. We can see the power cable is definitely warm going to the tea kettle. I don't see a whole lot of heat on the battery cables, the 4-aught cables going to the battery. You can see a little speck of heat there. I believe that's the MPPT charge controller glowing. Mostly it's just the inverter that seems to be glowing. It's interesting. We're down to 12.6 volts, 66 amps, 832 watts. You can hear that guy boiling. And again, interestingly enough, the power cable going to the kettle, the AC power cable, is glowing more than the 12-volt cable going to the battery itself. That dark cable in the background there is going to the battery itself. It's pretty interesting. Let's move the thermal camera a bit so that we can see the Battleborn battery more. Focus that. So there's the 4-aught cables on the battery. So it looks like that one is a little warm. Going to the, yeah, that's a little warm going to the DC breaker. Is it super warm? No, I can't even feel heat. So it's just warm enough that the thermal camera can see it. It's not warm enough for me to actually feel it. It feels cool to the touch. That is pretty cool. These cables are starting to glow ever so slightly. Not a whole lot. Let's go back and look at this. Let's look at the inverter. A little bit. Here's our inverter. Looks okay. It's glowing on the inside, but other than that, it looks all right. That cable that you see glowing there is the AC cable going to the GFCI. But everything else looks cool. I can see steam rising from the kettle now. There's the kettle. Bonavita. It just turned off automatically. And we should be able to see that also on the Victron. Yeah, we're back to 13.16 volts. So our voltage has dropped. We're only drawing 9 watts now. And boiling that 0.5 liters of water took 4.5 amp hours out of the battery. We're down to 94.9% capacity. Very cool. We're drawing 9 watts. So that 9 watts is from the MPPT charge controller. I think if I turn that off, okay, so 4 or 5 of those watts were from the MPPT charge controller. The remaining 5 watts is from the inverter itself. So if I turn that off, we're back down to 0 watts. Pretty awesome, huh? Man, that's real cool. So ending voltage, 13.21 volts, 94.9% capacity. We've pulled 4.5 amp hours. And from the thermal perspective, everything looks relatively cool. I'm not really seeing any problems with that. That glowing portion up there is from the MPPT charge controller head unit. And that glowing part right there is also the MPPT charge controller. It just tends to get warm when it's on, so not a huge deal. Let's look at the battery again. This is a, if you're curious, this is an iRay MH25 that I'm using for this thermal imaging. It is actually a helmet-mounted thermal camera. So it's got a viewfinder built in, but at the moment I have it on a tripod and I have it attached to a view screen, a monitor, and a recording device. It has a USB-C recording capability. It doesn't have the recording built in, unfortunately, which means I have this jumble of cables. But yeah, so that glowing part right there, that's the Blue Sea Systems DC breaker. It does not feel warm to the touch. So I'm not too concerned about that. I think that's fine for now. That was the hottest part of the system though, which is kind of interesting. I kind of wonder why. I wonder if one of my connections is a little loose. Doesn't seem like it. Yeah, it seems pretty snug to me. Not seeing any jiggle. I don't know why that's the hottest part of the battery. But I think I'm satisfied with that. I feel like there's a good chance that this system is not going to burn to the ground if I put some heavy loads on it. Seems okay to me. That bright cable there is again the AC cable going to the pot, the boiling pot, the kettle. It's interesting that the AC cable got hotter than anything else in the system. And putting my hand on it, even it doesn't feel particularly warm. Thermal camera is picking up on temperature gradients that I can't even feel with my hand. So, pretty awesome. All right, I'm going to turn off the thermal. Just to kind of back out here, if I can. That's our setup. Got the Bonavita pot right over here, full of boiling water at this point. And so let's do a little calculation here. So we did about 4.5 amp hours of power boiling 0.5 liters, right? 13.24 volts times 4.5 amp hours. That's roughly 59 watt hours of power that it took to boil 0.5 liters. Pretty interesting. I say roughly because I'm not really sure how that voltage part of the calculation works, considering that we started with a higher voltage and now we're on a lower one. But yeah, pretty cool. All right, this is Jesse with Create This. Hope you found this video interesting or useful. I'll probably have some of these items that I used in this video down below the video in the description. If you have questions about anything that I've done here, feel free to ask them down below in the comments. I usually reply to those pretty quickly. Depends on the comment, but I try to. I try to read them all. As always, thanks for watching, and please subscribe.